Okay. So the last thing that we were looking at yesterday was the sum and why this query, sum of x comma 3, where x is any list. We are asking Prolog to produce a list whose sum is 3, gave us an instantiation error. Essentially, this has to do with the fact that we had an is operator, and the right-hand side of the is operator is not a numeric term that Prolog can evaluate. It had a variable, right? And that was the issue. So we will continue seeing more examples that use lists in this class. Let me make this, let's see whether it's right. So, okay, so the next thing we are going to see is length of a list, right? So this is again a declarative reading. This looks very similar to how we would encode length in, say, OCaml, right? We would say length of an empty list is 0, and length of some list, right, which is non-empty, is n if the tail of the list has length m and n is m plus 1, right? So this underscore pattern matches with exactly one element. And what we're saying is, if you can show me that the length of the tail is m, then the length of the whole list with this whatever head that is, I don't care about that head, whatever head that is m plus 1, right? And we are using the same variable here. And so if you load this into Prolog and ask for length, it will give us 3, right? So this is not surprising. So this works as expected. So the reason for introducing this example is to show that there is this analog of tailed recursion in Prolog. Okay, so in OCaml, when we have a tailed recursive function, it is equivalent to a loop, right? We are not building up stack frames, so we can keep on doing that forever. And similarly, in Prolog, we have this optimization called the last call optimization. The idea is exactly the same. And the observation I want to make now is that this particular function is not tailed recursive. It cannot, Prolog cannot apply last call optimization on it. We will see why. So the intuition, if you can sort of see the intuition, we have a recursive call here, and then we have an arithmetic here. Recall that this is very similar to how we did non-tailed recursive factorial, right? We have some arithmetic that is left over after the recursive call returns, and similarly we have this length recursive call essentially, and then once that is satisfied, then you have to do this arithmetic, and let's see how that works out. Okay, so the observation is this implementation of len uses O of n stack space, where n is the length of the list. And let's do this by hand. So let's trace length of 2 by hand. Let me connect to my iPad. 0861. Okay. So what we're going to do is we're going to do len 1 to x, then 1 comma 2 x, right? So we are going to, this is our initial goal, and we have two options for this one, right? So as previously done, we have two clauses. So we're going to try the clause in the order in which they appear. So first thing we are going to do is to see whether this unifies with len of empty list comma 0, right? So empty list does not unify with list with 1 comma 2. So this comes back, right? So this is a failure. And then we try, what we do? Len of underscore, let me call it T2, N2 is len of T2, M2, N2 is M2 plus 1. Okay, so we have, sorry, so I wasn't, yeah, now you should be able to see what I've written. Just give me a shout if you can't see what I've written, right? So If I'm just talking over something which you're not able to see, just call me out and then we can fix it quickly. So we're going to try to unify this. Of course, we can unify the head. So this underscore unifies with 1, T2 unifies with singleton list 2, N2 unifies with X. Let's transfer these ideas, these unifications over to the right-hand side, the body of the rule. So T2 is a singleton list 2. M2, we don't know M2, right? That is unresolved. N2 is X, and that's all we know. We don't know anything about M2. So because the head has unified, we have two goals, right? And Prolog, which uses SLD resolution, picks the first goal that appears on the left to satisfy first. So this is going to be tried to be satisfied with len mt0, right? So this does not unify, right? Because we know that what we're trying to do is we see that T2 is the singleton list 2, right? But we are unifying with an empty list. So empty list does not unify with the singleton list. So we come back. Right. So let me actually make it explicit. So this comes back, this doesn't satisfy. And the next thing we try is the same rule, right? So it's going to look like len of T3 N3 is len of T3 N3 N3 is M3 plus 1. So now we are going to try to unify the goal that we have here with this one, right? So what do we do? So this underscore unifies with 2, T3 unifies with the empty list, and M2 is N3. So let's just write it out for convenience. M2. Okay, these are the unifications that we have. Let's transfer them over to the right-hand side. So T3 is empty list, right? We don't know what M3 is. N3 is M2. Okay, and now again we have to do this recursive call. So we go ahead and try len of mt is 0. So now if you focus on these two, right? T3 is an empty list. We are unifying that with an empty list. M3 is just a variable, so that unifies with 0. So the unifications that we have is this is T3 and 0 is M3. So we get this result back, right? So this will be 0, and we use these unifications to the next goal. So what we have there is M3 is 0. So now in order to satisfy this goal, we see that we have an is operator. So the right hand side must be fully ground numeric term, right? And it is, it's 0 plus 1. So Prolog computes the value of this numeric term and then unifies this with the term that is here. So we get 1, right? This is fully unified. And because we discovered that N3 unifies with M2 equals 1, we transfer this result over back to the head of the rule. So this is 1 now. Let's get it down, right? If you get it down, we know that M2 is 1. Let's transfer it over here. Now M2 is 1. So again, we have a is operator. So we see that the right hand side is a numeric operator. So that is 2. Oops. So this x becomes 2, right? 1 plus 1 is 1 plus 1 is 2. So this becomes 2. So you take this and move it to the head of the rule. So x is 2, and you bring it down. So x is 2. And that gives us the answer. And the thing that I want you to observe is that every time we did this recursion, right? We did this recursion, we have one goal that is left to do. And similarly, we had this recursion, we have one more goal left to do. And if you observe this, right, we have list with length 2 here, list with length 1 here, list with length 0 here. And you can imagine that if you have a list with length n, we would have n levels of recursion where we have something left to do afterwards. And this is the reason why this len clause, clause uses O of n stack space. Okay, so, and if you give it a large enough list, then this execution would stack overflow. So I'm not showing it because I'm not shown how to construct arbitrary length lists, but that's the idea, right? Any questions on that one? No questions? Okay. So in which case we'll continue, right? And the thing to do is write an analog of a tail recursive function in Prolog. So the way you do that is you use an accumulator, right? This is a standard technique that we use to make non-tail recursive functions tail recursive. So here is the len2, which is a tail recursive version of the length function for a list. So it says that len2, the fact len2 holds where if you given an empty list and an accumulator ACC, the length is going to be ACC, right? And if that's the base case for the recursion, and for the inductive case, if you give me a list with a non-empty list and an accumulator ACC, then the length of that list is going to be n. If m is accumulator plus 1, right? You first compute m as accumulator plus 1, and then you say len2 t mn holes. So this is basically the same idea as what we would do, right? We would say in OCaml, we would just write it as accumulator plus 1 here, but we can't do that in Prolog because in order to do arithmetic, we have to use the is clause. So we have to explicitly define some variable m is accumulator plus 1, and then we are just passing that accumulator plus 1 for the recursive call. So the observation here is that this arithmetic has been performed before we call len2 recursively, right? In the same way that OCaml optimizes tail recursive calls by popping the stack frame and then performing the call, Prolog also does something very similar. Okay, so this gives us the result that you would expect, right? And initially the accumulator is going to be 0. And just to show how this works, right, let's trace this one as well. So we are going to do len2 of 1, 2, 0, x, right? So we have these two clauses. So as usual, we'll try the first class first. So which is len2. So what we'll do is we'll do len2. So I'm going to name it as A1 because ACC is too long. So this we'll try to unify with this. Of course, this doesn't unify, right? Because empty list does not unify with 1, 2. So we come back. So I'm going to do x for this. And then I'm going to try to unify with the second one, which is len2 of h2, t2, a2, n2, m2 is a2 plus 1, then 2 of t2, m2, m2. Okay, so that is what I have, and this one unifies, right? So h2 unifies with 1, t2 unifies with singleton list 2, A2 unifies with 0, M2 unifies with X, and you transfer this over to the right hand side, and what you have is A2 is 0, right? So this has already unified. We don't know anything about M2 because that's an existential variable. We know something about M2, which is X. We know something about T2, which is this singleton list. We don't know anything about M2 here. So the important observation that I want you to take away is that observe that we can already do the arithmetic here, right? So the first thing we do is we actually finish the arithmetic, and M2 becomes 1, and M2 equals to 1. And what we have left now is this goal, and only this goal, right? And that's the last goal in the body, and that's the important thing. So in Prolog, you might have multiple goals, but if the recursion is on the last of the goals, then you can do last call optimization. So just to complete this, right? This one goes ahead and tries the clause with len2, empty, a3, a3. That would fail, right? That would come back as a failure because that doesn't unify. And then you try len2, h4, t4, a4, n4 is m4 is this one, n2, t4, m4, n4. Okay, so now you can unify this, right? H4 unifies with 2, T4 unifies with empty list, M2 is 1, so that unifies with 1 here, N4 is X, and if you transfer all of these results over here, then the unification result says that A4 is 1, T4 is empty list, M4 is, we don't know anything about M4 yet, N4 is X. And what do we have here? We again have an arithmetic that we can fully evaluate. So M4 is 2, and you transfer this over to the next goal, the last of the goals. So this becomes 2. So this is X, right? And now this unifies with the base case. So you take the base case, which is len2 of empty list, say A5, A5. This unifies with the empty list, right? M4 is 2, that unifies, and then we know A5 is X, and because we use the same variable A5, A5 here, this one unifies as well. And we directly have the result here, right? That's the observation. So once you unify, you have the result. And of course, we need to get it all down in the proof tree that we have to get it all down, but you can observe that as long as you keep the unification information around, right? You always keep this in a separate data structure somehow, this unification information. Once this is satisfied, you just need to look up the appropriate variables here. And this gives us x2. Okay, so so that's how, oops. And that's how we get tail recursion, right? By the fact that we do the arithmetic first and then recurs only on the last turn, we get tail recursion. Yeah, okay. So in Prolog, one thing you can do is because all of the predicates have an arity, right? We have something similar to predicate overloading. So if you look at the len2 predicate, it has arity 3, right? And then when we call, when we query len2, we have to explicitly pass this accumulator as 0. It is convenient. What we have done previously in OCaml is we've sort of hidden the 0 behind some other function name, right? We just redefine the function with the same name, where we call the previously defined function, where we pass the 0 explicitly. You can do the same in um, Prolog. So because Prolog fully distinguishes predicates not just by name but also by the arity, right? So what I'm doing here is I'm defining a predicate called len2, which has arity of 2, just has the list and the length x, which which is true if the len2 predicate that has 3 arguments, arity of 3 holes, where L is L, the first argument L is L, the second argument accumulator is 0, and the last argument um, X is X, right? And the way Prolog distinguishes these two is that this considers len2, this len2 as len2/2, and this is len2/3. And now you can, if you query len2 with just the 2 arguments, it will only look at unifying with this predicate, and that just gives us what we expect, right? So we get the result 3. Yeah, so that is last call optimization. So to summarize, right? So this last call optimization can be applied when the last clause of the rule is executed as a branch, not a call. So rather than so so what this means is that if you have a body with multiple goals, the last goal is actually not a call but just a jump. I mean, this is a bit of a technical term, the distinction, the difference between branch and call. But the idea is that because the last call is not going to leave anything on the stack, you can just jump to it rather than creating a new frame. Um, One caveat is that we can only do that if the rule is determinate up to this point. We haven't seen what determinate is. The idea is that just to give you an intuition, we'll see what being determinate is in the rest of the lecture. But the idea is that we say that the rule is determinate if there are no further choices for the rule. So in the proof tree that you built, recall that we had this idea where we explored one branch, but Prolog still had other things to explore. In Prolog, if you have such other things to explore, then we call that proof search tree not determinate. In order to apply last call optimization, it must be the case that there must not be other branches that you must explore, right? This relates to choice points, which we haven't fully formally seen yet. We will see this later, but keep that in the back of the mind. But otherwise, last call optimization is very similar to tail call optimization. Okay, so I'll pause here for questions. Any questions on what we've seen so far? It is either the case that you understand everything perfectly, or you don't understand anything at all. Because if you don't have any questions, it is very it can be only one of those two cases, right? um, Let me put it this way. Do you understand what is going on here? Yes or no? Right? You can put your messages in the chat. You have to ask some question, otherwise it just feels like I'm talking to an empty room. Really, no questions at all. So, a person who says yes will get 1% extra credit in the course. Okay, thank you. Satak has saved me. Okay, good. So, will we see a difference if ran trace on last column? Really good question, Satak. So, one thing that Prolog does, right? When you turn on tracing, is that it actually turns off the last call optimization. So I think I can show you this. Let's see. let me try to run this in the interpreter so that we can actually see whether this is the case. So I'm going to type this in the interpreter. It complains about singleton variable, but that's fine. And then I'm going to ask this query. Right. I'm going to turn trace on. I'm going to ask this query. So we have the initial call, which comes to this particular arithmetic, right, which works out fine. 1 is 0 plus 1 works out fine. And then it calls len2, right, which is the recursive call. So the thing that you want to observe here is we started at call 8, right? And then this number here is essentially the number of frames on the stack, Prolog interpreter stack. Okay, so the reason why it starts at 8 is because it has some system frames, right? Some boilerplate frames on the stack when you are evaluating. And the observation here is when we turn on tracing, Prolog helps us by turning off last call optimization. So that is why we see stack grow here, right? It started at 8 and it went to 9 and it went to 10 here. And yeah, so then it comes back, right? So really good question. So yes, so you won't observe, to answer your question, you won't observe the difference because Prolog turns off last call optimization. Okay, good. So let me continue. Yeah, okay. So the next thing that we are going to see is a few more functions. These this is perhaps the first function that sort of starkly tells you the difference between Prolog and the way we've been programming in OCaml, right? So far, the examples have been very similar to how we might have written the functions, equivalent functions in OCaml. So here is the first function that is going to look a little bit different. So we are going to do list append, right? The idea is that given two lists, list append tells you what is the result of appending both the lists. So we are going to write two clauses. The first one is the base case, right? The base case is very similar to the one that we do for in OCaml, right? So if the first list is empty and the second list is some list q, then the result list is going to be q. Okay, so because the first list is empty, the append of this list and the second list is going to be q, right? And the way to read this append, just a reminder, right? When you have three arguments, it says that when you appending first list and the second list gives you the result, right? That is what I want you to keep in mind. So the second clause is a little bit strange, right? It is different from what you might have seen earlier. So it says that let's say that the first list has a head h and a tail p, and the second list is q. Then the result list will have a head h and a tail r if it is the case that appending p and q gives me r, right? So you sort of take this h out, you have pq. If you append pq, if you get r, then if you put the h back onto p, then the result of appending the entire thing, these two things, is h appended to r. Sorry, h const to r. Right. So this is different from how we would have written it in OCaml. But if you just sort of stare at it, this must be obvious, right? So we have a h here, we take it out, and we say without this h, if p appended to q is r, then h const to p appended to q is going to be h const to r. Okay, so that's append, and now you actually see a good use of Prolog, right? So as I mentioned earlier, Prolog doesn't have input and output. We are only querying. So you can ask what is the result of appending 1, 2, and 3, 4. Prolog just comes back with 1, 2, 3, 4. You can also ask, let's assume that the first list is 1, 2, and the second list is something, I don't know. What is the list such that the result is going to be 1, 2, 3, 4, right? And Prolog computes that it's 3 and 4. And the beautiful thing that Prolog can do is you can also ask, you can leave both of these as variables, right? Both x and y as variables. And you're asking, what are all the combinations of x and y such that you can get 1, 2, 3, 4, right? So, and Prolog gives me all of the combinations. So it gives me empty 1, 2, 3, 4, right? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So that's yeah. So that is how yeah. This is really the first time we've seen the power of Prolog, right? We've actually seen Prolog produce something more than what OCaml would do, right? This is sort of similar to what we would have written in OCaml, except for how we've organized it. But the bang for the buck that you get with Prolog, right? We just write this function, we can query it in any order at all. So we can also get it as yeah, there is no input and output, so it can happily query any of these arguments. Yeah. Any questions on this? Okay, so if there are no questions, I'm going to proceed. So using this append, you can define additional functions called prefix and suffix. So the way to read prefix is, prefix and suffix operate on lists. So the way to read the predicate prefix is, x is the prefix of some list z, right? And y is the suffix of some list z. So when can x be a prefix of some list z? It can be a prefix if you can append x with some list y. I don't care about what this list y is, and you can get z, right? And that is the definition of prefix, right? And similarly, for suffix, we say that y is the suffix of z if you can show that there exists some list x, which when appended to y gives me z. Right? So I've handily defined the prefix and suffix predicates. So now I can query all the prefixes of, say, this particular list 1, 2, 3. So it gives me all the prefixes. So it gives me empty list, which is a prefix of 1, 2, 3, 1, 1, 2, and 1, 2, 3. And similarly for suffix, we have the opposite case. Right? So 1, 2, 3, 2, 3, 3, and empty. So imagine, and we would have to have thought about a prefix and suffix very differently if we had written in an imperative language. But because we are using a declarative form of encoding these facts, these things naturally followed. Okay, so the thing that we see here, and we also saw on append, is that Prolog is producing many results, right? All of these results are useful. And the question is, how is Prolog actually producing multiple results? The way Prolog produces multiple results is this idea called backtracking and choice points. This we've touched upon these ideas earlier, right? In your proof tree, you're going down one path, you might satisfy, but if there are other clauses that might also unify with the goals, then we call those sort of points, the goals where you can have multiple satisfying clauses, a choice point, right? And the way Prolog fetches multiple results is through backtracking. So what it does is it explores down one path of the tree. It might or might not find a result. If it finds a result, it produces the result, but also goes back and then erases all the unifications that it has done down that path, and then goes down the other search path, and then it finds other results, right? And that is how Prolog is producing multiple results, right? And the idea is that if there are no choice points left, Prolog has completely explored the proof tree, Then Prolog doesn't offer any more answers. It says, I've completely explored, and it comes back to the query prompt. This is the. Let's actually look at how this works for prefix, right? This is perhaps quite useful to see. So I'm going to trace prefix by hand. So what I'm going to do is I'm going to be very explicit, right, in how prefix works, just like how we've done earlier. But I'm also going to explicitly mark all of the choice points so that it becomes clear when things are actually choice points. So let me start with this. Uh, okay, I need to connect again. So 3170. Okay, so now um, okay, so what I'm going to do is I'm going to write down the goal, which is prefix x 1 comma 2, 1 comma 2, right? And how do we define prefix? So prefix x 1 comma 2 is what I've written down. And if you look at the definition of prefix, there is only one clause, right? And that is precisely append x yz. So I'm going to try to unify this with um, append um, x1, y1, z1, right? Um, Actually, I need to, sorry, I'm going to write it this way. I need to write it as prefix x1, c1 is append x1, y1, z1. Okay, so now x1 unifies with x, z1 unifies with 1 comma 2. So if you take these and write it on the body of the rule, z1 is 1 comma 2, x1 is x. Okay, so and y1 is the existential variable, right? Right. Yeah. Y1 is the existential variable, so we don't have any unification for that yet. But now if you look at append has two clauses, right? So let's try the first one first. So we are going to try to unify with append q2, q2. So the question is, does this unify, right? Um, does this unify? Yes or no? You can type the result in the chat. Yes, yeah. So it does, right? So all we have is we are going to unify this with x1. This is going to be y1, and this is going to be 1 comma 2. So because we are using the same variable q2 here, we have the result, right? So we know we have the result. I'm going to use a different color now, just because I'm going to undo all of this later. Okay, so this comes back. What we have, we found that um, x is empty, right? Y1, this is y1, so this is going to be 1 comma 2. Says the only variable that we have here is x, so this is x, and we are going to come down. And what we have is we have the first result, right? This is why the first result that we saw for prefix um, here is the empty list, right? Because we've defined the proof tree by the rules of Prolog, and we saw that the first result that we got was the empty list, and that's why we have the empty list. The important thing that I want to write down is that we had a choice point here, right? I'm marking that goal because append has two clauses, and we've unified with the first clause. It worked out. We can also unify with the second clause. So let's do that. So now what Prolog is going to do during backtracking is that it has produced the result for the first one, right? It is essentially going to undo all of these unifications, right? It's going to undo this. It's going to undo this, undo everything that was obtained because of this one, right? And you consider the way Prolog makes sense of this is, let me consider this to have failed, right? If it has failed, the resolution has to continue with the second clause. So I'm going to continue with the second clause. So it's going to try, let me write it down. Append H3, P3, Q3, H3, R3, S, append Okay, so this is what I have, right? Now I'm going to try to unify these two terms, right? The term that is here, the goal that I have here, and the head of this clause, right? It turns out you can unify this, right? The way to unify this is this whole thing, right? This whole thing is some compound term, but what we have here is just a variable. So that happily unifies. So this unifies with x1 equals x. I'm not writing it down. Q3 unifies with y1. And for the last term here, we see that this is 1, 2, right? And hence H3 unifies with 1, R3 unifies with the singleton list 2. So if you transfer all of this information over to the body, we don't know what P3 is because P3 is still not unified with anything useful. Q3 is also, let's just leave it as Y1 here, right? And R3 is the singleton list 2, right? So now so this continues, right? And what we have, we'll try to unify this with append empty Q4, Q4. Okay, so now, now this unifies, right? So this is P3, this is Q3, and R3 is the singleton list 2. So this is singleton list 2, and this is singleton list 2. And now we need to bring it down. Again, I'm going to use a different color. So if you do this, what do we know? We know that Y1 is 2, right? And if you substitute, and P3 is the empty list, right? And if you look at these rules and bring it back here, we know that Y1 is the same as Q3, which is 2, right? And what we know about H3, this H3 here is 1, right? So we can write this as 1. And what is P3? P3 is the empty list, right? And if you sort of look at this term, right, it is 1 appended to empty list. So x1 is going to be the singleton list 1, which you bring down, right? And x1 is the singleton list 1. You get it here, singleton list 1, and you get it down. That becomes the singleton list 1. And that's the second result for the prefix, right? So if you look at this one, you have the second result. And you can keep doing this, right? And the way to keep doing this is you sort of observe first that when we took a choice here, there was a choice point, right? And you keep erasing everything that you've done in gray. So you sort of take all of these unifications out, this out, this out, right? And these unifications out. Um, and you consider this to be a failure, right? And now we can again try the second clause for append. And if you do that, you will get 1, 2. And finally, this will terminate, right? So I'm not going to continue this fully, but you can observe that that will terminate. Actually, we know H1, H3 is 1 here. So we can write H3 is 1. Yeah. But otherwise, you can keep doing this. And what Prolog essentially does is it keeps doing this over and over again, right? And as long in the Prolog interpreter, as long as you keep pressing semicolon, it will keep exploring more and more choice point. Actually, whenever Prolog stops, right, presents a first result and stops, it is essentially saying, okay, I found a result for you. There was a choice point. Do you want me to continue exploring down the choice point? Right? And when you press semicolon, it is undoing, it is backtracking all of the unifications that it's done and exploring the choice point further, right? And this is essentially how Prolog produces multiple results, right? And the sort of things that you want to keep in mind is where is the choice point, right? When you see a bunch of rules, if you stop at one of the clauses and you have further clauses, the idea is that you make sure that further clauses are also explored, right? And every time you match with the first clause and there are further clauses, there is a choice point. Yeah. What else did I want to say? I think okay. So that is my that is what I wanted to say about prefix, and I have to cover this in the next class. But you can think about this, right? So imagine you have this len function that we had defined earlier. Len of empty is 0, and then len of non-empty list is this whole thing. What I'm doing here is usually we give the list and ask for the length. I am asking for what is the list A such that its length is 2, right? So abstractly, if I were asking you, you will say that it is any list which has 2 elements, right? It doesn't matter what the content is. It is just any list which has 2 elements. But I'm asking a specific question. What will Prolog say, right? What is the first result of the query where len, the query is len a comma 2? So which one of these will be the answer? Work it out. We'll have a look at it tomorrow, right? So there are some interesting observations here because of how Prolog works out the results to these ways. Okay. Try it in your if you have time today, you should try this out. Okay, cool. So I'll stop here. Any questions so far on this? Okay, so wonderful. So in which case I'll stop and then I'll see you tomorrow. Bye bye.